Okay, everybody, halfway through week 5, we're getting into section 4.7. And in 4.7, we need to talk about inverse trigonometric functions. Okay, so these are the objectives. We're going to talk about the inverse sine, cosine, and tangent. Learn how to evaluate these guys using a calculator, and also talk about composite functions with these guys. Okay, so these are the examples we want to use. Before I talk about the examples, though, let's go through this idea here. So first of all, I hope you remember that only functions that are one-to-one have inverses, right? That means they have to pass a horizontal line test. A horizontal line can only pass through them once, right? For every value of y, there can only be one value of x. So it's a stronger function than just a function. So what we have to do is, that's not the case for sine and cosine, right? Sine and cosine, like this is the sine function I have dotted here on this side, and it would go on forever and ever and ever, but then a horizontal line would pass through an infinite number of times. So we need to restrict the domains of the trig functions. Now, what people have decided to do is restrict the domain of the sine function between minus pi over 2 and pi over 2. So here's the sine function between minus pi over 2 and pi over 2. And then the full line here, then not dotted line, is the inverse sine function. So this is y, which is sine inverse of x, this graph right here. Now notice that's just like inverse function notation. That does not mean 1 over sine of x, so just be careful. And then the other thing that happens is the domain and range swap. So since the domain of minus pi over 2 to pi over 2 for sine, the range for inverse sine is minus pi over 2 to pi over 2. That's all because it's reflected about the line y equals x, right? And the range of sine is minus 1 to 1, so the domain of inverse sine is minus 1 to 1. And you can see that in this picture. Likewise for the cosine. Now the cosine we can't restrict between minus pi over 2 and pi over 2 because that also would not pass a horizontal line test. So we have to restrict the cosine between 0 and pi. So this is the restriction of the cosine between 0 and pi, which makes the inverse cosine look like this guy. And you can see reflected about the line y equals x, how it would look. And the domains and ranges of these guys flop, right? So the domain of cosine is 0 to pi, which makes the range of cosine inverse 0 to pi. The range of cosine is minus 1 to 1, so the domain of the cosine inverse is minus 1 to 1. But that's an idea of what those guys look like. Now, if we look at the tangent function, there's no need to restrict, ooh, geez, I wrote these backwards. Restrict the range and domain of tangent, sorry. The domain of tangent is minus infinity to infinity. Cross that out. The domain of tangent, right? It can be anything. Oh, no, I'm sorry. Yes, well, I apologize. We had to restrict it. We had to restrict the tangent between minus pi over 2 and pi over 2. Remember, it would not pass a horizontal line test. It repeats over and over again. So we're just taking the one piece of tangent that is in the middle here, not the repetitive parts. So the domain, yes, we do restrict it from minus pi over 2 to pi over 2. And the range, though, stays from minus infinity to infinity, which is a nice thing because that means the domain of the inverse tangent is now minus infinity to infinity, and the range is minus pi over 2 to pi over 2. So the domain of the inverse tangent is all x, which is nice because that's not true for the other functions. Okay, so before I get into the examples, remember the following, that if I take the function of its inverse, evaluate f of f inverse of x, out should pop x. Likewise, if I take f inverse of f of x, out should pop x. But for the trig functions, we also have to consider where the domains of the functions are, especially since we had the restricted domains of sine, cosine, and tangent in order for the sine inverse, cosine inverse, and tangent inverse of x functions to exist. So for example, if I want the cosine inverse of the cosine of 9 pi over 4, you intuitively might just say, oh, that's 9 pi over 4. But that's not correct because we had to restrict cosine between 0 and pi. So I have to find a coterminal angle. So here's 9 pi over 4, but also notice that pi over 4 has the same terminal ray. So in other words, its cosine, sine, etc. will all be the same. So coterminal angle between 0 and pi of 9 pi over 4 is pi over 4. So cosine inverse of the cosine of 9 pi over 4 is really pi over 4, since the cosine of pi over 4 is the same as the cosine of 9 pi over 4. Pi over 4 is in the proper restriction of the domain, however. Okay, what about an example like this? Let's say I want the secant of the inverse tangent of minus 4/7. So what I have to think about is, how do I look at this inverse tangent of minus 4/7? And if I have the inverse tangent of some number, what that is asking for is what angle, that's an angle, what angle theta has a tangent That's minus 4/7. So I have to remember that tangent had to be restricted between minus pi over 2 and pi over 2. And then where would tangent be negative? Down here in the fourth quadrant. Draw in the angle I'm looking for. And again, I actually don't even need to know the angle because I eventually want just the secant of that angle. But I do need to know the sides of its reference triangle. So tangent is opposite over adjacent. So that has to be minus 4 because it's in the negative y direction. So minus 4 over 7. That allows me to figure out the length of this hypotenuse, just using Pythagorean's theorem. It comes out to be the square root of 65. So now the secant of that angle, using the reference triangle, secant is 1 over cosine. Cosine is adjacent over hypotenuse, so the secant is hypotenuse over adjacent, square root of 65 over 7. Now I just apply the same procedure whether that's a specific number or not, or an algebraic expression. So now it's an algebraic expression, but I'm going to apply the same procedure. I want the cosine of the sine inverse of 2 over x. Okay, so we assume x is positive, which puts the sine inverse, we know that sine had to be restricted between minus pi over 2 and pi, so I'm assuming x is positive whenever I'm not told. Assume it's positive. So then that would mean that sine is opposite over hypotenuse, so 2 over x. This is the angle whose sine is 2 over x. The angle theta whose sine is 2 over x. That gives me these two sides of the triangle, which then using the Pythagorean theorem tells me that this side has to be the square root of x squared minus 4. So the cosine of that angle whose sine was 2 over x is now adjacent over hypotenuse, square root of x squared minus 4 over x. And as a last example, let's say we know that theta is 2 times the tangent inverse of 21.634 over x. And what we want to do is understand that this is actually a model of a viewing angle theta in radians for a camera whose lens is x millimeters wide. So first of all, you're told that it's in radians. We want to find the viewing angle in radians and then in degrees of a 72 millimeter lens. So 72 millimeters, that's x. So plug that in for x. Then I want to use the tan inverse button on my calculator. Make sure you can use the tan inverse button. Make sure it's in the radians mode so that your answer comes out to be 0.2919 radians. Multiply that by 2, this 2 here, so you get 0.5838 radians. Now if you want to change that to degrees, we just multiply it by 180 degrees over pi radians. But they told you this formula was in radians, so your calculator has to be in radians mode. Make sure that you can understand how to use the tan inverse button. Make sure you know that your calculator is in radians mode. Practice, make sure you do get 0.2919 when you plug this into your calculator.